Hey everyone, it's been a while since my last video. I took a bit of a break, but I'm super excited to be back and diving into something a lot of developers use but not always fully understand. Chances are that if you are building modern applications, you have already used OAuth2 or OpenID Connect. Most of us integrate it in our apps, set up a client ID, secret, maybe tweak some scopes, but not always know why we are doing it or how it really works. In this video, we'll strip down to the basics so you finally get to know why OAuth2 and OpenID exist and how they secure your applications. Stick around, it's simpler than it looks, and you will actually understand what's under the hood. So let's get started. Before we dive into OAuth2 and OpenID, let's quickly rewind to how things worked before these standards were around. Imagine you are building a web app and you want users to sign in. The most straightforward way, just create your own login form, right? The users type in their username and password, you save that in your database, and next time they log in, you check it again. But here's the problem. Now you are responsible for storing and protecting everyone's password. That means dealing with password hashes, salts, data leaks. And if your app gets compromised, attackers get direct access to actual login credentials. And what if your app needs to talk to another service on behalf of the user, like pulling emails from the Gmail or files from Dropbox? Well, you would have to ask them for their Gmail password directly. That's a huge security and trust nightmare. If your app leaks that password or you store it poorly, you have now compromised someone else's Google account. So clearly, we need a better way. A way to let your app do things on your behalf of the user without ever seeing their password. And that's exactly the gap OAuth2 and later OpenID came in to solve. Let's start with OAuth2. What exactly is OAuth2 trying to fix? It's mainly about authorization, not authentication. In simple words, it lets your app do things on behalf of the user without ever handling their password. Think of this like, imagine you want to give a delivery person access to drop off a package at your house. You don't have to hand over your main door key, right? Instead, you might give them a temporary access code or leave the package in a smart lock. They just get enough access to complete the delivery, nothing more. That's basically what OAuth2 does. It lets an app, like your app, to get permissions to access the specific data, say users' Google Drive files or post to their Twitter account. All this without seeing their password. This is done through something called as access tokens. The user logs in on their actual Google account or Twitter page. They see a consent screen that, hey, this app wants to read your files. Is that okay? If they say yes, your app gets a special token, like a temporary pass. This token only allows what user has approved. It might be reading the files but not delete them. And it expires after some time or can be revoked by the user at any point. So that's why OAuth2 became so important. It gives users control over what apps can do and kept passwords completely out of their hands. Way more secure for everyone. So OAuth2 is all about authorization, giving an app permission to act on users' behalf. But what if your app needs to know who the user is? Like you want them to log into Google and then simply greet them by their name on your site. That's where OpenID Connect or OIDC in short comes in. OIDC or OpenID actually builds on top of OAuth2. It uses the same flows, same tokens, but adds a new type of token called ID token. This ID token is usually a JWT, that's a JSON Web Token. The OAuth2 spec doesn't actually require access tokens to be JWT. It just says access tokens is an opaque string that the resource server understands. ID tokens are always JWTs by OpenID Connect spec. But in many modern implementations, access tokens are also JWTs like Azure AD, OAuth0, Okta, etc. It's cryptographically signed by identity provider like Microsoft, Google, or your IDP. Inside the ID token, you will find claims, things like users' ID, email, maybe their name or profile picture. Your app can trust this info because it is signed, so you know it really came from Google and not someone pretending. Here's where scopes come back into play. In OAuth2, you would ask for scopes like read drive files or post on Twitter. In OpenID Connect, you ask typically for OpenID scope. Without it, the provider thinks you just want access token. When you include OpenID, it knows that to also give you ID token that tells you who the user is. So to sum it up, OAuth2 lets you access the APIs on user's behalf. OpenID lets your app actually learn who the user is in a secure, verifiable way. And the cool thing, it's all part of the same redirect flow. You're just adding one more scope and handling one more token. Since both ID tokens and many access tokens are often JWTs, let's quickly break down what a JWT looks like. A JWT basically has three parts separated by dots. You will see something like this. Those three parts are header, payload, and signature. The header usually says what algorithm was used to sign it, like RS-256, and it's a JWT. The payload is the main data, also called claims. It might include subject, email, name, issued at, expires at, audience, issuer, like claims. And finally, signature. Signature is created by hashing the header and payload together with the provider's private key. Your app uses the public key from the JWKS URI to verify the signature and make sure that the token wasn't tampered with. What a JWKS URI is, we'll discuss in a while. Using the keys in this URI, that's how your app knows, yeah, this token really came from the IDP and it hasn't been changed. When working with OAuth2 and OIDC, you'll also come across some config bits in your app setup. Let's decode these. If you have already worked on it before, you would probably have seen things like client ID, secret, scope, and redirect URI. The client ID is your app's public ID. It is how the provider like Azure AD, Google, or your IDP knows which app is making the request. The client secret is like your private password for the app. You will use the secret on the server side of your app to prove that your app is legit, especially when you exchange the authorization code for tokens. Scopes tell the provider exactly what your app wants. Could be something like drive.read-only or calendar.events, or for OpenID Connect, just the OpenID email and profile to say, hey, I want to know who this user is and get me some profile info. And the redirect URI is where the provider will send the user back after they log in and give consent. To get started, we need to get our app registered with the identity provider and the redirect URI for our application. This must exactly match the URL where you want the IDP to redirect back, or the provider will block it during authentication to prevent attacks from stealing tokens. So let's see how this all actually works in practice. We'll look into the authorization code flow, which is the standard for web apps. On a high level, your app redirects to authorization endpoint. The user authenticates themselves with identity provider. The identity providers redirect back to the app with an authorization code. The app uses this code to get the token using token endpoint. That may sound like a lot of new things with these endpoints, codes, and tokens. Also, you must be wondering, how does my app even know where to send these users to log in? Or where do I exchange these codes for tokens? Let's thank to something called as well-known configuration. It's a special JSON document exposed by all these identity providers. You will find the URL to this document something like domain name /wellknown/OpenID configuration. Like for Google, it's accounts.google.com/.wellknown/OpenID configuration. For AD, for Azure AD, it is like login.microsoftonline.com/the tenant ID /v2/wellknown/OpenID configuration. Your app or library fetches this document and it spells out all the important endpoints, which looks something like this. Authorization endpoint. This is where your app should redirect the user browser so that they can log in and approve your app's access. Token endpoint. Your backend calls this to exchange the authorization code you receive for an access token and ID token. User info endpoint. Post login, if you want more user info beyond what is there in ID token, your app can call this with access token. JWKS URI. This is where your app finds providers' public keys, so it can verify the signature on ID token and maybe on access token, making sure that it really came from the IDP. And there are other information also like supported scopes and claims, but these are the core ones which are mostly used. So in most libraries, you just configure the issuer URL and it automatically discovers everything it needs from this well-known config. Now let's go back to the authorization code flow. To start with, your app redirects the user to the authorization endpoint. It builds a URL using the data from the well-known config and includes the client ID, scope, the redirect URI, and a random state to protect against ESRF. Once the app redirects to identity provider, the user sees the provider's login screen, like Google or Microsoft or your own enterprise login. They enter their credentials, which your app never sees. Now, during the first login, they may see a consent screen like this app wants to read your profile and calendar. You want to allow. The user provides the consent to complete the authentication process. The user gets sent back to your app using the redirect URI which the app provided when redirecting to authorization endpoint, along with a temporary authorization code in the URL. Remember the authorization code we talked about for token exchange? This is exactly the code we were talking about. Your backend exchanges this code for tokens. It makes a secure post request to the token endpoint, which it learned from the well-known configuration, sending the authorization code, client ID, secret, and redirect URI. If everything checks out, the provider returns an access token, so your app can call the APIs, and an ID token, which proves who the user is. Your backend validates this ID token. It checks the signature on the ID token using the public keys it downloaded from the JWKS URI. That's how it knows the token really came from the IDP and not from someone who was trying to fake it. Now, your app can show user's name or maybe the picture from the ID token and use the access token to make API calls on their behalf. It's secure because the client secret stays on your backend and the token never touches the browser beyond the short-lived authorization code. And you must be wondering, what about single page apps like React, Angular, or Vue? They don't have a secure backend many times to keep the client secret. That's where PKCE comes in, proof key for code exchange. It lets browser apps securely do authorization code flow, proving that the app that started the flow is the same one finishing it in scenarios where they can't store the secret securely. Here is how it works. Your app generates a random string called code verifier. It's usually a high entropy string, that is a sequence of characters that exhibits a high degree of randomness and unpredictability, making it difficult to guess. So the code verifier could look something like this. Then your app creates a code challenge by hashing the verifier with SHA-256 and then doing a base64 URL encoding on it. It might look like this. This way, the code challenge is public, but only your app knows the original code verifier. When your app redirects the user's browser to the authorization endpoint, it adds two extra parameters, the code challenge and the code challenge method, which is equal to S256 always. S256 tells the provider you are using SHA-256. The only other valid option usually available is plain, which makes no sense to use. So the full URL might look something like this, with the authorization endpoint and the parameters required for the request. After the user logs in and approves the consent if needed, the provider redirects back to the app with authorization code. Now your front end doesn't have a secret, but so it makes a post request directly to the token endpoint, sending the authorization code along with the code verifier. So instead of client secret, it is sending the code verifier. The provider takes this code verifier, hashes it on their side, and checks that it matches the code challenge you sent earlier. If it matches, they send back tokens. The access token, so you can access APIs, and ID token to know who the user is. This means that even if someone intercepted the authorization code in the browser, they could not swap it for tokens without also knowing the original code verifier. That's why PKCE is such a game changer for a single page application. It replaces the client's secret in a way that's secure, even if everything runs on your user's browser. Now that we have seen how the flow works, let's talk about where developers often get it wrong. First mistake is they just trust the ID tokens they get back from the provider. Remember, an ID token is a signed JWT that says like this user is bob@example.com verified by Google. Your app should always validate the signature using the public keys provided using JWKS URI. If you skip this, anyone could craft a fake ID token saying they are admin@example.com and your app would accept it. Next mistake is ignoring the state parameter. The state parameter is a random string your app sends when it redirects the user to authorization endpoint. When the user comes back to your redirect URI, you make sure the same state comes back. This protects against ESRF attacks. If you don't check it, someone could trick the user into authorizing on your app's behalf without ever visiting your site. Another one is developers often confuse access token with ID tokens. They are for different purposes. The access token is meant to be sent to your own backend or something like Google Drive or Microsoft Graph API. The ID token is just for your app to know who the user is. You typically never send this to other APIs. Treat them differently. They have different audiences and different security models. Also, don't forget to check the expiration time of your tokens. ID tokens and access tokens are short-lived for a reason. If your app keeps them using forever without checking the EXP or the expiry claim, it's an open door if someone steals it. And then there is storing the tokens insecurely. In single-page applications, a lot of people just dump the token into a local storage. That means any JavaScript running on your page, including malicious scripts from an XSS attack, can grab the token. It's usually safer to keep the tokens in memory if possible and to always sanitize and secure your apps against excesses. If local storage isn't safe, where should I actually store my tokens in front end? The best approach is to keep them in memory only. That means your access token and ID tokens just live in some JavaScript variable for the lifetime of the page. Because even if your user later visits a malicious site or some dodgy browser extension installed, those tokens are already gone if they closed your apps tab. Now sure, this does mean if they refresh, they would technically lose their session. That's fair. Most OAuth libraries like MSAL, OAuth2 Okta use silent authentication behind the scenes. They just open a hidden iframe or use a still valid session at identity provider to get the fresh token without bothering the user again. Some people try session storage, which at least clears on tab close, but remember it's still accessible to any JavaScript running on your page. So if you have an XSS vulnerability, that token can be stolen. And if you are working with a backend, you can use BFF pattern, backend for frontend. The backend stores the token in an HTTP only secure cookie, so your frontend never sees it at all. That's as secure as it gets. There are other types of authentication types, and also called as grant types in OAuth2 world. Let's quickly look at some and when you might actually use them. First is the client credentials grant. This is used when there is no user involved at all, like a backend service calling another backend API. Your app sends its client ID and secret directly to the token endpoint and gets back access token. It's purely app-to-app authorization, great for microservices, jobs, or machine-to-machine communication. Then there is device code flow. This is used for devices that can't open a browser easily, like a smart TV or a command line tool. The device shows a code to the user. They just visit a URL on their phone or computer, enter the code, approve the app, and then the device gets a token. Next is resource owner password credential grant. Basically where the user gives your app their username and password directly, and your app trades that for a token. Sounds convenient, right? But it's not actually recommended anymore because your app now handles the user's raw password, exactly what OAuth2 was trying to avoid. You would only see this in legacy systems or trusted first-party apps where the app and identity provider are basically the same. We should not be using it anymore. Next is implicit flow, which was specifically designed for single-page applications that couldn't safely store secrets. In this flow, instead of providing an authorization code while redirecting back to the app, the IDP provides the ID and access tokens in the URL as query params. But today, it's considered outdated and less secure because tokens are returned straight in the URL fragment, making them more exposed. That's why PKCE with Authorization Code Flow has replaced implicit flow in most single-page applications. So the big takeaway for applications here is that for backend apps or backend web apps, use authorization code flow with client secret. For single-page applications, use authorization code flow with PKCE. For backend to backend, use client credentials, and avoid implicit and ROPC unless you have a really solid reason. After all this, you might be thinking, do I have to write all these redirect URLs, codes, challenges, token validations myself? Thankfully, no. There are tons of solid libraries that handle these flows, signatures, silent renewals, and token validations for you. They follow the OAuth2 and OpenID specs and have been battle tested by thousands of apps. So whether you are building a React app, or a .NET app, or a Node.js app, there is a library for you. I'll drop a list of some of the most popular ones down in the video description, so you can pick that fits your stack. That brings us to the end of this video. That's it for today. I hope now you are not just integrating OAuth2 and OpenID Connect, but actually understanding why and how they work. If this helped clear things up, give it a thumbs up and maybe share it with your team so that they also understand it. Got more questions? Drop them in comments and I would love to help you out. And if you would like, I can also do a follow-up video where we actually implement this step by step in, say, a .NET app or an SPA. So if that's something you would want to see, just drop a comment below and I'll put it together. You can also follow me on social media platforms for updates and more content like this. Links are available in the description box below. Thanks for watching and see you in the next video. Until next time, keep coding smart and keep innovating. Adios.